In section 5, we're going to talk about roots, rational exponents, and simplifying radicals. So first one we're going to discuss is square roots. So the definition of a square root, so the square root of some number a equals b if b squared equals a. So basically trying to figure out what number squared is giving you a, and that's the square root of a. So some properties of square roots. Every positive real number technically has two square roots, one positive and one negative. Because if you think about it, if I square -4, I get positive 16. And if I square 4, I also get positive 16. So that's why you can have one positive and one negative. We are going to focus, when it comes to square roots, we're going to focus on positives. The square root of 0 is 0. And then when we use the square root symbol, we can also call it a radical if we are specifically talking about the non-negative square root of a real number. So the non-negative square root is called the principal square root, and then the number underneath the radical is called the radicand. So for example, the radicand in the square root of 25 is 25. And then also for any real number c, such that c is greater than or equal to 0, if I square the square root of c, I get c. So if you think about it, a square and a square root undo each other. So if I square a square root, I'm just left with what was underneath the square root to begin with. So let's look at some examples. So our first example is the square root of 16. So I already kind of did that as an example. So the square root of 16 we know is 4, since 4 squared is 16. We have negative square root of 64. So the negative on the outside means I take the square root of 64 and then I multiply it by that negative, which is going to give us -8. The last one is the square root of -9. So in this case, it's not a real number, and at this point, it's not going to have a solution. We'll talk about later in Module 4 if we have a negative underneath the square root and how that works. We also have perfect square roots. So the examples I just did were for perfect square roots. So it's a number whose square root is a whole number. So that means it's not a decimal. So for example, the square root of 49 is 7 because it's a perfect square, but the square root of 2 is actually a decimal. It's about 1.414. So 2 is not a perfect square root because it doesn't give me a whole number when I take the square roots. Just a couple more properties. The square root of a perfect square is a rational number. And the square root of a positive rational number that is not a perfect square is called an irrational number. So for example, the square root of 20 is irrational because 20 is not a perfect square. We're also going to discuss cubic roots. So we talked about this a little bit when we were doing the sum and difference of cubes formula. So a cubic root is when you have the cube root of some number a equals b if b cubed is a. And then that works for any other root, 4th root, 5th root, 6th root. Just keeps going for any root you're taking. So for example, cube root of 0 is going to be 0, just like the square root of 0 is 0. Now, I can take cube roots of negative numbers. So I can't take the square root of a negative number, but I can take the cube root of a negative number. So the cube root of -8 is actually going to be -2. Because if I do -2 times -2 times -2, I'm still going to get a negative number as my answer. And then our third example, cube root of -64x to the 6th. So we are also going to introduce variables when we're talking in terms of square roots and cube roots and so on. So I take this cube root of -64 like normal, which in this case is going to be -4. Now when it comes to variables, it works a little bit differently. So x to the 6th is x times itself 6 times. And when we're talking about cube roots with variables, we look for groups of whatever root we're taking. So if I'm taking a cube root, I look for groups of 3, which in this case, there are 2 groups of 3, which means the cube root of x to the 6th is x squared. So for exponents, you divide by the root you're taking. So 6 divided by 3 is 2. But for numbers, you figure out what number cubed gives you that. All right, so in general, so we can generalize this. We've done cube roots, we've done square roots, so now we can generalize. So if I take the nth root of some number a, and it gives me b, as long as b to the n equals a. So we just generalize it for any root. We're going to mainly focus on square roots, cube roots, fourth roots, and fifth roots. Those are the 4 that we're going to focus on. Very rarely will I give you a root higher than that. So for example, cube root of 27, I want to find the number that when I multiply it by itself 3 times, I get 27, which is going to be 3. 625, I want to find its fourth root. So the number that times itself 4 times is 625, which is going to be 5. And then I have the cube root of x to the 6th. So as we've already discussed, that's going to be x squared. We also are going to deal with fractional exponents. So these are also known as rational exponents because we are dealing with a fraction. So if I have a, so some number a, raised to the power of 1 over n, that is the same thing as saying that a to the 1 over n is the same thing as the nth root of that number. So fractional exponents where the numerator is 1 is another way to write a root, which we kind of discussed a little bit when we were talking about the beginning of the module 3 when we're talking about is this a polynomial or not. So we're seeing it again here defined. So that means that if I do 4 to the 1/2, I'm looking for the square root of 4. If I do 27 to the 1/3, I'm looking for the cube root of 27. So just a couple examples, rewriting and then simplifying if possible. So 25 to the 1/2 is saying square root of 25, which we know is 5. 27 to the 1/3 is the cube root of 27, which is going to be 3. And then lastly, I have x to the 1/5, which is just saying the 5th root of x, which that can't be simplified because I have 1x, 1 does not divide into 5 evenly. I can also do an example where I have a to the m over n. So instead of my numerator being 1 in my fraction, it can be any number m. So a to the m over n, it's still the nth root of a, but a is also raised to the power of m. So you can either write that m inside the radical or you can write it outside the radical. It doesn't matter if it's inside or outside here in terms of the exponent. So our first example, we have 9 to the 3/2. So that means I'm taking the square root of 9 and I'm cubing it. Now when it comes to the order of simplifying here, I can either cube that number first so I can raise it to my exponent, or I can take the root. And I'm actually going to take the square root here. It's always easier to simplify the root first, then raise it to the exponent. So the square root of 9 is 3, and then I'm going to do 3 cubed, which is 27. My second example, we have negative 32 raised to the 2/5. Now the negative being inside parentheses here is very important. It means that the negative travels with the number. So I'm taking the 5th root of negative 32, and then I'm going to be squaring it. So the 5th root of negative 32 is going to be negative 2, and then I'm going to square it, and I'm going to get a positive 4. If the negative had been outside, so if I had negative 32 to the 2/5 and the negative is on the outside, the negative stays on the outside. So it becomes negative 5th root of 32 squared, which becomes negative 2 squared, which becomes negative 4. So the location of the parentheses is very important here because it does change our final answer. Right, last example, we have 1/4 to the 3/2. So I'm taking the square root of 1/4, and then we're going to cube it. So the way I take roots of fractions works the same way. I take the square root of 1, which is 1. I take the square root of 4, which is 2, so I get 1/2, and then I'm going to cube it. And the way I applied my exponent is I apply it to both the numerator and the denominator. So 1 cubed is 1, 2 cubed is 8. And then the last thing that we're going to discuss is negatives in my exponent. So I have a to the negative m over n. And negative exponents doesn't actually mean you get a negative number. What it does is it changes it to a fraction. So a to the negative m over n is the same thing as 1 over a to the m over n. So all you do is you convert it to a fraction. And then you apply the same rule as you did for a to the m over n. So 27 to the negative 2/3, I'm first going to rewrite as 1 over 27 to the 2/3, which is then going to become 1 over the cube root of 27 squared. The cube root of 27 is 3, so we have 1 over 3 squared, which gives us 1/9. Our second example, here's an example where my negative is not inside parentheses. So I have negative 256 to the negative 3/4. So my negative is not going to travel with the 256. So first I'm going to write it as negative 1 over 256 to the 3/4, which becomes negative 1 over the 4th root of 256 cubed. The 4th root of 256 is 4, so we have 1 over 4 cubed, and 4 cubed is 64, so we have 1 over 64. So far, all of the examples we've done with radicals have been perfect squares, perfect cubes, perfect fourths, so on and so forth. But that's not always going to be the case. So when that happens, we have a different method of simplifying. So for example, just to refer a radical, we're talking about the nth root of any number a. So what we're going to also discuss is the product property of radicals. So if you have two numbers a and b, which are both greater than 0, and I have the nth root of a times the nth root of b, I can go ahead and multiply those and I get the nth root of a times b. Now, important thing here is n has to be the same. So I can't do the cube root of 2 times the 4th root of 7. I can't do that. N has to be the same. So I can only multiply radicals if they're the same root. So when it comes to simplifying radicals, what we do is we write the radical in terms of its non-perfect root factors. So that means we basically break it down to its multiplication of its prime number. So this is also kind of referred to as prime factorization. So we break it down to the multiplication of prime numbers. So let's look at some examples. So first example, we have the square root of 18. So I'm going to start breaking down 18 in terms of its multiple. So numbers that multiply to give you 18. So there's a couple different choices here you can do. So the first one that comes to mind for me is 9 and 2. Then 2 is a prime number, so I'm done breaking that down, but 9 is not. It breaks down as 3 times 3. When we are looking to see how we simplify the radical, the root we're taking determines how many of the same number we have to have in order for it to come outside the radical. So in this case, because of a square root, we look for groups of 2 of the same number. So I have 2 3s here, which means I can bring a 3 outside the radical, and then anything that doesn't have a friend, I like to call it, or a pair, stays underneath. So in this case, my 2 stays underneath the radical. So the simplified version of the square root of 18 is 3 square root 2. For 288, I do know it's an even number, so I'm going to first break it down as 144 times 2. 144, I know, is 12 times 12. 12 is 6 times 2. And 6 is 3 times 2. So I've broken it down to all of the prime numbers that multiply. So now I'm looking for groups of 2 of the same number. So they don't have to be off of the same branch. So look here, I have a group of 3s here, and I have a group of 2s. And then I have another group of 2s here. So I have a group of 3 and 2 groups of 2. So if I have multiple numbers that are going to come outside my radical, I multiply them together. So I have 3 times 2 times 2. And then underneath my square root, I still have this lonely 2 from up top. So 3 times 2 is 6, times 2 is 12. So I get 12 square root 2. Next, we have 5 times the square root of 54. So for 54, I know that's 9 times 6. 9 breaks down as 3 times 3. 6 breaks down as 3 times 2. So I have a pair of 3s. So that 3 has to come outside and multiply with the 5 that's already there. So it's going to be 5 times 3. And then underneath the square root, I have a 3 and a 2 that are going to multiply back together. So I have more than one number that's left without a pair, so they multiply as well. So I get 15 square root 6. Right, so now we're going to look at the cube root of 54, x to the 4th. So I can break down 54 the same way I did when it was a square root, 9 times 6, and then 3 and 3, and 3 and 2. But in this case, because I'm looking at a cube root, I need 3 of the same number. So if I look here, I do have 3 3s. So I'm going to bring a 3 outside my root. I also need to look at my variables. So I have x to the 4th. So if I'm thinking how many groups of 3 are there in x to the 4th, there is one group of 3. So I'm going to have an x. Then underneath my cube root, I still have a 2. And 4 doesn't divide into 3 evenly, so I also have an x left over. So 3x cube root of 2x is going to be my final simplified answer. Just a few more examples where we practice more with variables. So I have the square root of 25 a to the 4th b to the 9th. So 25, only one way to break that down, 5 times 5. So there's a pair of 5s. A to the 4th, there are 2 groups of 2 there, so I have a squared. B to the 9th, I have 4 groups of 2. And then underneath the square root, there is still a b because 9 is not divisible by 2 evenly. X to the 7th, y to the square root of x to the 7th, y to the 8th, z to the 9th. So how many groups of 2 are there in x to the 7th? There are 3. There are 4 groups in y to the 8th, and then there are also 4 groups in z to the 9th. And then underneath my square root, I still have 1x and 1y, since 7 and 9 are not divisible by 2. And the last example, the fourth root of 32, a to the 9th, b to the 20th. So 32 I can break down as 8 times 4. 4 breaks down as 2 times 2. 8 I can break down as 4 times 2, and then 4 is 2 times 2. So in this case, because it's a fourth root, I need 4 of the same number. So there are 4 2's right here. So I'm going to bring out a 2. When I look at a to the 9th, there are 2 groups of 4, so I get a squared. And then for b to the 20th, there are 5 groups of 4, so I have b to the 5th. Underneath my fourth root, I still have a lonely 2, and there is one a, since 9 is not divisible by 4. So what I want you to go ahead and do now is pause the video and simplify the following ones on your own. And then once you're done, go ahead and continue playing the video to get the answers. So for the square root of 81 y to the 5th, I can break down 81 as 9 times 9, which then is 3 times 3 and 3 times 3. So you have 2 groups of 3, which are going to multiply on the outside. Then y to the 5th, there are 2 groups of 2 in that. And then underneath the square root, I still have a y. So my final answer is 9y squared square root y. For the cube root of 24, a to the 9th, b to the 4th, I'm going to break it down as 8 times 3. It is not the only way you can break it down. 8 is 4 times 2. 4 is 2 times 2. So I have 3 2's that I can bring outside my cube root. A to the 9th, there are 3 groups of 3, and b to the 4th, there is 1 group of 3. And then underneath my cube root, I still have a 3 and a b. And the last example, fourth root of 32 x z to the 7th. So 32, I'm going to break down as 8 times 4. 4 is 2 times 2. 8 is 4 times 2, which is 4 times 4. Sorry, 2 times 2. So fourth root, I need 4 2's. So there's going to be a 2 on the outside. Z to the 7th only is divisible by 4 with 1 group. And underneath the fourth root, there is still a 2, and there actually ends up being 3 z's left over. So 2z, fourth root of 2z cubed. So now we're going to talk about multiplying radicals and simplifying them afterwards. So my recommendation for these is to always multiply first and then simplify. Even if a radical can simplify first, after you multiply, you still have to check to see if it simplifies again. So instead of having to simplify more than once, I always wait until the end to simplify. So we have the square root of 3 times the square root of 5. Because they're both square roots, I can just go ahead and do 3 times 5, which gives me the square root of 15. Which does not simplify because the only way to break down 15 is 3 times 5, which are both prime numbers. So that's my final answer. Next, we have the square root of 6 times the square root of 21, which becomes the square root of 126, which I do need to simplify. I don't have to come up with 2 brand new numbers to simplify 126. Since I multiplied 6 and 21 to get it, I can first break it down as 6 times 21. 6 is 2 times 3. 21 is 3 times 7. So I do have a pair of 3's that are going to multiply that I can bring outside. So I have 3. And then underneath the square root, I have to multiply my 2 and my 7 since they were left without friends. So I get 3 square root 14. Lastly, we have the square root of 8x cubed times the square root of 6x. So I'm going to go ahead and multiply. 8 times 6 is 48. X cubed times x is x to the 4th. So I break down 48. I can break it down as 8 times 6. 8 becomes 4 times 2, which then 4 becomes 2 times 2. And then 6 becomes 2 times 3. So I notice I'm going to have two groups of 2 here, which are going to multiply on the outside to give me 4. X to the 4th, I can simplify completely to x squared. And underneath the square root, I still have a 3. So I get 4x squared square root 3. All right. 2 times the square root of 12xy cubed times 3 times the square root of 30x squared y. So not only if you're multiplying radicals do you have to multiply what's underneath them, but if there's anything out front, you have to multiply those as well. So 2 times 3 is going to give me 6. Then 12 times 30 is 360. X times x squared is x cubed. Y cubed times y is y to the 4th. So I'm simplifying it. I can break down 360 as 12 times 30. 12 I can break down as 4 times 3. 4 is 2 times 2. 30 I can break down as 5 times 6. 6 breaks down as 3 times 2. So I have a group of 2's and I have a group of 3's. So on the outside I already have a 6. I have to multiply by the 2 and the 3 that I'm bringing outside. For my x cubed, I have one group of 2, and for my y to the 4th, I have two groups of 2, so I get xy squared. Underneath my radical, I still have a 2 and an x. So 6 times 2 times 3 is going to give me 36 xy squared square root 2x. So far, all of the examples we've done have been square roots, but I might throw in a cube root for multiplication as well. So the cube root of 16m squared n to the 4th times the cube root of 40mn. So I'm going to do 16 times 40. So I'm going to get the cube root of 640. M squared times m is m cubed, and then n to the 4th times n is n to the 5th. So break down 640, I can break it down to 16 times 40. 16 is 4 times 4, which breaks down as 2 and 2 and 2 and 2. 40 I can break down as 10 and 4. 10 breaks down as 5 and 2. 4 breaks down as 2 and 2. So when it comes to selecting groups, I look for groups of 3 of the numbers, 3 of the same number. So I have 3 2's, and then I have another group of 3 2's. So 2 times 2 on the outside is going to give me 4. M cubed has one group of 3 in it. N to the 5th also has one group of 3. So I have 4mn. Underneath the cube root, I have a 2 and a 5. They're going to multiply back together to give me 10. And then I'm going to have 2 n's left as well. So my fully simplified answer is 4mn cube root 10n squared. The last thing that we're going to talk about is adding and subtracting radicals. So when we're adding and subtracting radicals, you can only add and subtract like radicals. So when we say something is like radicals, it's any radical or radicals, so any radicals with the same root and radicand. So for example, the square root of 2 and the square root of 2 are like radicals. They're both square roots and 2 is underneath. The cube root of 3 and 7 cube root of 3 are also like radicals because they're both cube root 3's. But the square root of 2 and the cube root of 3 are not like radicals because they have one square root and one cube root, and also they're not the same underneath. It also works the same way if you're looking at the same root. So like the square root of 2 and the square root of 5 are not like radicals because even though they both have the same root, they don't have the same radicand. So one of them is the square root of 2 and the other is the square root of 5. So when it comes to adding and subtracting radicals, if they're already like radicals, you can go ahead and add them. But you still have to check to see if what's underneath the radical can simplify as well. So for our first example, we have 5 square root 15 plus 2 square root 15. So when you are adding like radicals, you only care about the numbers outside the radicals. Those are the things that combine. The like radicals you can think of as variables. So you can also think of this as 5x plus 2x, which we know becomes 7x. So it works the same thing with the radicals. 5 square root 15 plus 2 square root 15 is 7 square root 15. You're basically saying, how many square root 15s do I have? And there are 7 of them. For our second example, we have 9 cube root 2y minus 15 cube root 2y. So again, I only care about the 9 and the 15. My cube root 2y's are going to stay the same. So 9 minus 15 is going to be negative 6 cube root 2y. And in both of these examples, 15 and 2y are as simplified as they can get. So I didn't have to worry about simplifying those radicals. The last two examples we're going to look at is what happens if I don't already have like radicals. It doesn't mean I can't combine anything. What it means is I have to simplify my radicals and see if they simplify to like radicals. So I have square root 20x minus 6 square root 16x plus square root 45x. So I'm going to simplify each of my radicals. So 20 I break down as 5 times 4, which 4 breaks down as 2 times 2. So the square root of 20x becomes 2 square root 5x, because I still have a 5 and x doesn't simplify. 16 I can break down as 4 times 4, which becomes 2 and 2 and 2 and 2. So I have two groups of 2 here, which have to multiply with the 6 that's already out there. So it becomes 6 times 2 times 2, which gives me 24 square root x, because there's no number left underneath, but I still have my variable x. And then 45 I can break down as 9 and 5, and then 9 is 3 and 3. So I have a group of 3's. So it becomes plus 3 square root 5x. So I only have 2 like radicals here. I have my 2 square root 5x and my 3 square root 5x. Those are like radicals. So those I can combine. So 2 square root 5x plus 3 square root 5x gives me 5 square root 5x. But I still have my minus 24 square root x. It just didn't combine with anything. My last example, square root 50 minus square root 18. So 50 I'm going to break down as 25 times 2. 25 breaks down as 5 times 5. So I have 5 square root 2. 18 I'm going to break down as 9 times 2. 9 breaks down as 3 times 3. So I have minus 3 square root 2. So now they are like radicals. So 5 square root 2 minus 3 square root 2 is going to give me 2 square root 2. I know we covered a lot in section 5, so if you have any question about any of it, whether it's simplifying radicals, multiplying radicals, or adding and subtracting radicals, please let me know.